All right, good afternoon. Uh, Again, yesterday we were resuming with functions, more specifically working with quadratic functions as well as their features, and and in reference to what we have in the first section of the second chapter, we have on page 249, and again, there are two kinds of displays that commonly occur when expressing a function that is quadratic. One is the standard form, and also that which we looked into yesterday we have with the vertex form. And again, we have with the vertex form, we have like y is equal to f of x, or k of x is equal to a times k the square of x minus h, followed by the addition of k. And for what we have on page 249, in the case of number 10, okay, we're looking at various features that we have regarding the function k of x, which we have set equal to 2 times the square of x minus 3, followed by the subtraction of 2. And again, we're looking at the direction the graph is going to open, as well as the vertex, and also the intercepts. So again, in terms of the dynamics that will be carried out, okay, so we have for A, okay, that is going to be represented by 2. Okay, so you have that A is equal to 2. Okay, and here, okay, A is positive. And so we're going to have right away, okay, for what we have in part A. Okay, so you have A is equal to 2. And we have that A is positive. So in this case, the graph of k of x is going to open upward. For what we have now for the axis of symmetry, then we have for part F, and also in the case of the vertex in part B, okay, we're going to need the value of h, and later the value of k. Okay, so we have for x minus h, okay, that is represented by x minus 3. Okay, so if I set that which represents x minus h equal to 0, okay, so we have x is going to be equal to 3. So for your h value, okay, that's going to be the resulting x value, okay, from setting this binomial equal to 0. So I have x is equal to h is equal to 3. And for what we have regarding the k value, okay, so we have the subtraction of 2 at the end. So we have that k is equal to negative 2. Okay, so we have, again, with the axis of symmetry, and I'm just going to kind of stress this, but just in terms of the axis of symmetry, again, you're taking the binomial x minus h and setting that equal to 0. You have x equal to h. So again, we have the axis of symmetry in the general case at x is equal to h. And we have, in this specific case, we have that x is equal to 3. So we have for the axis of symmetry for this item, okay, we're going to have that x is equal to 3. And for what we have in the case of the vertex, okay, so you have the coordinates hk. Okay, so again, we have h is going to be at 3, and the k value is at negative 2, so the vertex is going to be 3, negative 2. Now, for what we have in the case of parts C and D, okay, we're now looking at the determination of the intercepts. Okay, so we have, say, in the case of part C, okay, in determining, okay, just what the x-intercept or intercepts will be. Again, for each x-intercept, we're solving for x as that which we have in y is going to be set to 0. Okay, So we have with our function, okay, so we have y is equal to k of x is equal to 2 times the square of x minus 3 followed by the subtraction of 2. And again, k of x represents y, and I'm going to set this equal to 0. And you could square out x minus 3 and then solve for x in that fashion through the pathway of utilizing the zero product property. But what I'm going to do here is that I'm just going to isolate the variable expression here. So I'm going to take 2 from the far right and undo the subtraction by adding. So we're going to have that 2 is equal to 2 times the square of x minus 3. And we have in following through. Okay, so if I divide by 2, okay, so we have that 1 is equal to the square of x minus 3. Okay, so in this approach, okay, I'm sort of setting things up for the square root property of equality. And what I'll do here, I'll just switch the order. Again, just reverse the terms. Have what was on the right to be on the left, and vice versa. Okay, so we have x minus 3 squared is equal to 1. And again, just kind of going back to the square root property of equality. Okay, so here we have x represented by x minus 3. So if I go from the square of x minus 3 to just x minus 3, I'll just drop the degree from 2 to 1 in essence. So we have equal to plus or minus the square root of 1. And so we have x minus 3 is equal to plus or minus, and the square root of 1 is 1. So we're going to have, in the case of the values for x, so we're going to have on the lower end, we're going to have the x minus 3 is equal to negative 1. And on the upper end, okay, we have x minus 3 is equal to 1. And looking at isolating what we have for x, so if I add 3 to both sides in both equations, okay, for x minus 3 is equal to negative 1, okay, so we're going to have the x is equal to 2. And for x minus 3 is equal to 1, okay, we're going to have the x is equal to 4. Okay, so we're going to have a couple of x-intercepts. And as Alex would probably have your x-intercepts, you would express as x is equal to 2 and x is equal to 4. But like in the textbook, and also to put on display in coordinate fashion, x equals 2 refers to the ordered pair 2, 0 on the x-axis, and for x equal to 4, we're going to have 4, 0. So in terms of coordinates, the x-intercepts we have at 2, 0 and 4, 0. Okay, now in the case of what we have regarding the y-intercept, okay, so you have a role reversal in terms of what to set equal to 0 and what to solve for. All right, and so we have in this particular setting, okay, so again, k of x is another way of saying what we have for y. And whenever we have x set equal to 0, okay, so we're looking at whereupon we're going to have that y is equal to k of 0. That is when x is 0. And so we're going to have 2 times so 2 times 0 minus 3 quantity squared, followed by the subtraction of 2. And so we have 2 times the square of -3. All right. Now looking at squaring all of -3 here, so I have -3 squared is going to be at 9. And 2 times 9 is 18. Take away 2. So we're going to have for the y-intercept, okay, this is going to be at y is equal to 16. And for what we will have in coordinate fashion, okay, it's going to be the ordered pair 0, 16. Right. So you have 3 intercepts altogether. Okay, so we have 2 on the x-axis at 2, 0, and 4, 0, and 1 on the y-axis, okay, where we have at 0, 16. Right. So again, we have for the components, okay, so you have the axis of symmetry, x is equal to 3. The vertex, okay, we have at 3, -2. Now the graph opens up, so this vertex is going to be the location, it's going to be the quadratic function's minimum, okay, and we have the x-intercepts at 2, 0, and 4, 0, and the y-intercept we have at 0, 16. And for what we have in terms of the display here, and see if I can so just taking what we have here. Okay, so we have for the graph of the quadratic function, okay, so I have in red, okay, so you have this parabola that is opening upward, and okay, and we have the axis of symmetry, okay, which we have at x is equal to 3, and just looking at what we have among the features, okay, so we have the vertex we have situated at 3, -2, and the x-intercepts we have at 2, 0, and 4, 0, and the y-intercepts, okay, we have at 0, 16. And let's say if I were to supply any additional points without having to do any calculating, again, you can use the axis of symmetry. Okay, notice you have 2, 0 is one space to the left, 4, 0 is one space to the right. And if we go up, say, on the axis of symmetry, level with the y-intercept, okay, so we're going to have, again, the axis of symmetry. Okay, we have at x is equal to 3. And if I were to supply a point that is level with the y-intercept, okay, so the y-intercept is going to be 3 spaces to the left. And if I go across and go 3 spaces to the right of the axis of symmetry, and again level with the y-intercept, you can go from x equals 0 to 3 to x is equal to 6. So among the infinitely many points that the graph of this function has, along with the vertex and the intercepts, we have 16 also in the mix. All right, now for what we have in the case of number 12, and we have this time we're going from k of x to r of x. And in this one case, we have r of x is equal to 1/2 of the square of x plus 2. Okay, so we have, again, in the general layout for the vertex form, so in 12, okay, so I have r of x is equal to 1/2 of the quantity of x plus 2 raised to the second. Okay. So we have, just looking at the components here, so we have a is equal to 1/2. And again, x minus h is represented by x plus 2. So if we look at solving for the h value, Okay, so I have x plus 2 set equal to 0. So we have that x is equal to negative 2. And again, we have x is equal to h is equal to negative 2. And notice, okay, we don't have anything added or subtracted after 1/2 times the square of x plus 2. So there's a void. So that signals that the value of k is going to be at 0. Okay. So in terms of what we have among the features, okay, so the value of a is 1/2. Again, we have that a is positive. So this means that, like what we had with k of x in number 10, we have r of x in number 12 is going to open up from the vertex. And for what we have in the case of the axis of symmetry, okay, again, the axis of symmetry always passes through the vertex point. Okay, so the axis of symmetry, okay, that's going to be at x is equal to negative 2. And for what we have in the case of the vertex, for the vertex, okay, so you're going to have your hk is going to be equal to negative 2, 0. And that is going to end up on the x-axis. And for what we have with the x and the y-intercepts, now the x-intercept is going to be a bit kind of redundant, since you're going to end up with the x-intercept and the vertex being one and the same. But I just wanted to mention something. Okay, so you have that representing y, we have it r of x. We'll set this equal to 0. So you have it's equal to 1/2 times, okay, the square of x plus 2. Okay. And if I multiply the equation by 2, okay, so 2 times 0 is still 0, and 2 is going to take care of the 1/2, so I have 0 is equal to the square of x plus 2. And again, I can just switch the order, like b is equal to a, same logically as a is equal to b. And we have with the square root property of equality. So if I go from the square of x plus 2 to just x plus 2, and guess what? There's no positive or negative 0. The square root of 0 just remains locked in at 0. There is such a thing as like positive and negative infinitesimals, like numbers very, very close to 0, but that's not what we're dealing with. Okay, so again, we have x is equal to negative 2. So you have the x-intercept, we have x equal to negative 2, or in coordinate fashion, we'll have a negative 2, 0, where that is also the vertex. And in the case of the y-intercept, okay, so again, we're looking at solving for y whenever x is set to 0. So this time around, we're going to have that y is equal to r of 0. Since I'm setting x to 0, so I'm looking at 1/2 of 0 plus 2 quantity squared. Okay, so I got 1/2 of the square of 2. And 2 squared is 4. And 1/2 of 4 comes out to 2. Okay, so now y is equal to 2. And again, just for the y-intercept, okay, we're at y is equal to 2. and just taking what we have and putting in ordered pair terms. So we have at 0, 2. All right. And in terms of what we have in the graphing display. Right. So you have like 2 points that are distinct. Okay, the vertex and the x-intercept happen to be one and the same. And we have a y-intercept at 0, 2. And just looking at what we have, let's say for the graph itself. I think I do have this one in store. Yes, okay. Okay, and I put some other points up as well, but just for key items, again, the vertex, we have a -2, 0, and the y-intercept we had at 0, 2. And again, just for the axis of symmetry, again, that was at x is equal to -2, so just looking at what we have here. So the axis of symmetry passes through the vertex. If you notice going up, now the y-intercept, okay, now this is going to be like 2 spaces to the right, okay, and I have it, this happens to be scaled in increments of 2, so you have like each square horizontally moving, it'll be 2 units. So you got 2 units to the right, and then 2 units to the left across from the y-intercept. I end up 2 spaces to the left the axis of symmetry. So I have a -4, 2, and if I were to go up, say, any further, say if I have like, what's going to be 6 spaces to the right, I have 418, and level with 418, if I go 6 spaces to the left, I have -8, 18. So again, the axis of symmetry visually divides up the graph of the parabola into equal mirroring halves. Okay, so you have, so at each level along the axis of symmetry, again, the right and left hand sides of the function will be equal in distance from that dividing line. Okay, now, and looking at the items we have with functions, and what we'll do here is that for number 17 and number 20, I'm going to be looking at just converting from the standard form to the vertex form and identifying the vertex. To identify the other features like the intercepts and all that, there are going to be some irrational roots in the mix, and I'll show you like a case with number 18, but for what we have in the case of number 17. Okay, we have a function p of x and we have is equal to 3x squared minus 12x minus 7. And if I'm looking at translating from standard to vertex form, okay. So here we have the standard form. Now if we look at converting in terms of the vertex form, again, like the other day, okay, I separated the variable terms apart from the constant. Okay, so the variable terms, we have a 3x squared minus 12x. So we'll put parentheses around these first 2 items. Okay, so you have 3x squared minus 12x minus 7. And again, yesterday there was an approach referred to as the completion of the square. Okay, and when we complete the square, okay, what I said was to make sure that the first term in the parentheses is x squared and that there's no coefficient other than 1 in front of the x squared. But here, we have 3 out at the front. So any coefficient that you have in front of x squared or whatever square term you have, factor out that leading coefficient. So in this case, right, so I'm going to factor out 3. And so we're going to have in the rewrite, so I'm going to have p of x, and taking out 3, so you have 3 times. 3 will go into 3x squared times. 3 will go into negative 12x minus 4x times. You have minus 7. Okay, now with the first term inside the parentheses at x squared, okay, I can proceed with, again, the completion of the square. Again, so the first term inside the parentheses, upon factoring out 3, okay, we have to be at x squared. And with the completion of the square, okay, again, so you take what is next to x. In this case, you have the number negative 4. And regardless of whether it is a fraction, a whole number, integer, non-integer, you're going to take half of what is next to x. So next to x, we have negative 4. Take half of that and then square. So half of negative 4 is negative 2. And negative 2 squared is equal to 4. Right. So as we proceed, okay, so we have p of x. We have is equal to 3 times the quantity. Okay, so you have x squared minus 4x, and with 4 resulting from the completion of the square. Okay, so we have plus 4, which again will be used to form this square trinomial. Now, for what is going to happen now before, whenever the first term was x squared and x squared alone, whatever I added to the front, I subtracted at the back. But now with the 3 out in the front, okay, there's an added dimension here, because as I am adding 4 inside the parentheses, what I'm doing overall at the front is that I'm actually applying 3 times the addition of 4. So I'm in effect adding 12. I'm adding 12 to the front. So to keep it balanced, instead of taking away 4, I'm actually going to have to take away 3 times 4. So I'm going to take 12 away from negative 7. So here I'm going to have p of x. Okay, so this will be 3 times x squared minus 4x plus 4, and negative 7 minus 12, okay, this will become negative 19. And you can pretty much double check too. If you multiply by 3, you got 3x squared. 3 times negative 4x is negative 12x. 3 times 4 is 12, and then in turn 12 minus 19 comes out to negative 7. So we're in balance. So for the vertex form, okay, now we got 3 times, and for x squared minus 4x plus 4, we now have a square trinomial, and the negative 19, this is going to end up as our k value. And okay, so for x squared, again, this is going to be the square of x, and once again we have with the square of negative 2. Okay, that which we squared to get to 4, okay, was negative 2, and that's going to re-enter the scene. And so it's going to result that for what we have in the vertex form, we have 3 times the square of x minus 2, followed by the subtraction of 19. Okay, so that'll be the resulting vertex form in this one. Okay, now I'll get to number 18. If I tell you what, if we look at number 20, okay, and we'll just look into the vertex form on this one as well. Okay, now for the case in number 20, okay, so we have our function, okay, which will be d of x. And we have that d of x is equal to negative 3x squared minus 9x plus 8. Okay. And, okay, so we have with the standard form. Okay, so this is going to be the standard. Okay, and once again, I'm going to separate the variable terms apart from the constant. Putting the variable terms once again in parentheses. Okay, and if you notice, okay, we have inside the parentheses, okay, the first term is not x squared, but negative 3x squared. Notice earlier I had 3x squared and I factored out 3. Now over here, I'm going to factor out negative 3. And for this, now this is a tricky item in terms of converting to vertex form. So upon factoring out negative 3, okay, so negative 3 into negative 3x squared, so this would be x squared. And negative 3 into negative 9x, okay, that's going to be a plus 3x. Again, you can double check. Negative 3 over x squared is negative 3x squared. Negative 3 over 3x is negative 9x. And again, we have plus 8. And now, with the first term in the parentheses, now at x squared, I can proceed with the completion of the square. Okay, so with the completion of the square, again, I'm going to look at what is next to the first order x, and that's going to be the coefficient 3. And again, just like what I did with negative 4 earlier, I'm going to take this time positive 3. Again, take half of it and square. Okay, so for 3 halves squared, okay, so 3 halves times itself, okay, this is going to end up at 9/4. So in comparison, okay, now this is going to be a trickier one because we're now dealing with a fraction. So now we have negative 3 times the quantity. Now we have x squared plus 3x, and now we're going to have 9/4 to be added. Again, we have plus 8. Okay, and for the dynamics that are being carried out, okay, it says I'm adding 9/4 within the parentheses. It is at the front. I'm not adding just 9/4, but adding negative 3 times 9/4. So we have in the overall picture, you got negative 3 times Negative 3 times 9/4, so this will be negative 27/4. So at the front, I'm subtracting 27/4, and to override the imbalance or the deficit that is created at the front, I'm going to add the same amount at the end. Okay, so we have 8 plus 27/4. And for what we have in the case of d of x, so I have negative 3 times the quantity, so you have x squared plus 3x plus 9/4. Okay. And for 8 plus 27/4. You can say we have like 8 over 1. It's 27/4. Least common denominator would be at 4. Okay, so 8 is going to be at 32 over 4. And adding to 27/4. So we're going to have a non-integer value with 59/4. Okay, so this is going to be what is added at the end. And for what we have in the follow through. Okay. So we have with d of x, you got negative 3. And again, we have with x squared, okay, so that's going to be the square of x. Now the k value is already going to be at 59/4. And again, that which we squared out earlier to get to 9/4. Okay, again, this is going to resurface. So we have negative 3 times the square of x plus 3/2, followed by the addition of 59/4. And so we're going to have for the vertex form, we have negative 3 times the square of x plus 3/2 plus 59/4. So this is going to be the vertex form. All right. Okay, so now in the case of what we have with number 18, so just kind of going out in the full-fledged performance on this one and identifying not just the vertex form, but also just some of the identifying characteristics. And we have for this item, we had the function in the form of q of x. Okay, and so we have we got q of x, okay, and in the standard form, so we have 2x squared minus 4x minus 3 so this is the standard form. And if I translate what I have into the vertex form, so I'm going to separate the variable terms apart from the constant. Okay, if you notice inside the parentheses, okay, we have the coefficient 2. So, and you could factor out in advance if you can see the pattern already. And we have, upon factoring out 2 at the front, so we're going to have q of x is equal to 2 times the quantity of x squared minus 2x. And then we have followed by the subtraction of 3. Again, you can check 2x squared minus 4x, and then we have minus 3. And once again, we can complete the square. And again, for that which is next to the first order x, again, we're going to take half of this and square out, so half of negative 2 is negative 1. And we have negative 1 squared, okay, is equal to 1. And 1 is going to be added within the trinomial. Again, since I factored out 2, I'm not just adding 1. So as I'm adding 1 inside the parentheses at the front, I'm adding 2 times 1. So I have at the front. Okay, so you got the 2. If I didn't have to factor out anything, I would be adding just 1, and I could just offset the surplus by subtracting 1. But here, I have instead adding 2 times 1. So to override this surplus, I'm going to take away the same amount at the back. And so we're going to have that q of x, okay, is equal to 2 times, okay, the quantity of x squared minus 2x plus 1. And then we're going to have for the k value, okay, that is going to be at negative 5. And so just taking what we have here, yeah, I had to keep things charged. Okay, so you have 2 times the quantity of x squared minus 2x plus 1. Now for the vertex form, so you have q of x, I have equal to 2 times. Okay, for x squared, that's going to be the square of x. Again, earlier, I squared out negative 1 to get to 1. So this is going to be 2 times the square of x minus 1, followed by the subtraction of 5. Okay, so this is going to be the vertex form. Okay, and that was for part A. Okay, and in terms of identifying the key elements here, okay, and we have okay, so we have with the vertex form, so your A value is going to be at 2. X minus 1, okay, have a reference to x minus h. So if x minus 1 is equal to 0, okay, we have x is equal to 1. So you have the x is equal to h is equal to 1. And in terms of what we have for the k value, okay, k value is equal to negative 5. Okay, and in taking what we have here, you're just kind of skipping around. Okay, we have with the axis of symmetry. Okay, so you have x is equal to 1. And for the vertex, again, you have your HK, so that's going to be a 1, -5. All right. Now, in terms of the follow-through, and the reason I'm kind of throwing this in, okay, so I went with the standard form as well as the vertex form. So I converted from standard to vertex form. Now, in terms of the intercepts, you can use either form to find out the intercepts. And let me just mention, okay, so again, we have with the standard. Okay, so you have that q of x, okay, is equal to 2x squared minus 4x minus 3. And the vertex form again, so we have q of x is equal to 2 times the square of x minus 1 minus 5. Okay. And okay, now for finding out the x and the y intercepts, you can approach with either one of these particular forms. And let's say that in the case of the x-intercepts. Okay, so the x-intercept, okay, now you're setting y equal to 0. And what you can do here is that, at least with the vertex form, okay, you don't have to do all the trinomial factoring. So we can go with the vertex form on this one, but you can choose either approach. And we'll go with the vertex form on this one. So say we have 0 is equal to 2 times the square of x minus 1 minus 5. And just taking what we have here. Okay, so going with the vertex form, so if I isolate the x expression, okay, so I can add 5 to both sides. So we have that 5 is equal to 2 times, okay, the square of x minus 1. And what's going to happen here is that if I divide both sides of the equation by 2, okay, so I have 5 halves equal to the square of x minus 1. And I'll just switch sides, just like in the case of numbers 10 and 12. So we have with the square root property of equality, so if I go from the square of x minus 1 to just x minus 1, okay, now you don't have perfect squares with 5 or 2. What I'm going to do here is that for the square root of 5 halves, okay, that's going to be the square root of 2.5. And say to about the nearest 3 decimal places, this is going to be about 1.581. So looking at the approximate values for x, so you have x minus 1 equal to negative 1.581 on the lower end, and on the upper end we have x minus 1 is equal to 1.581. And if we solve for x upon adding 1 to both sides, So we have the x is equal to negative 0.581. And we have adding 1 to 1.581. Okay, we have the x is equal to 2.581. So you're going to have a couple of x-intercepts. And if I were to display what I have in coordinate fashion, okay, so it's the nearest 3 decimal places. These would be our ordered pairs. And I was going to mention for the y-intercept, so here for the y-intercept, I could use either the standard form or the vertex form. And if I set x to 0, I can get to the y value rather quickly. So I'm just going to choose the standard. So if I choose the standard, so I have that y is equal to q of 0. And guess what? So I got 2 times the square root of 0. Minus 4 times 0 minus 3. Guess what? These terms are negligible. 0 minus 0 is 0. 0 minus 3 becomes negative 3. So we have that y is equal to negative 3. So for the y-intercept, we have y is equal to negative 3. And in terms of ordered pairs, we have the location at 0, negative 3. So you got 3 intercepts, 2 on the x-axis, 1 on the y-axis. And just to kind of show what we have here. And again, just for this particular function, again, we have the parabola is going to be opening upward. Okay. Again, we have the axis of symmetry. Again, whereupon we have x equal to 1. So the vertex, we have the location at 1, negative 5. Again, we have the y-intercept at 0, negative 3. And on the x-axis, again, we have the ordered pairs. So you have negative 0.5810, 2.5810. And if I were to add any other points, again, you're going to have symmetry with respect to the vertical line, the axis of symmetry. So going up, you have like 0, negative 3. And so you have like 1 space to the left and 2 negative 3s, mean 1 space to the right. So you're going to have proportion throughout. Okay. And personally for me, I like it when the intercepts have integer values, not the irrational roots like what we had just a moment ago. But I just wanted to at least show one of these to kind of reveal some of the dynamics that play out. And sometimes the intercepts don't always come out cleanly to whole numbers or integers, and that happened to be one of those situations. All right, now looking at what we have for the next item, and we'll be looking at what's going to be referred to as multiplicity. And for what we have in this phase, okay, so we have we'll call this part forming polynomials. from given zeros and multiplicities. Okay. Now for what we have regarding multiplicities. Okay, now the multiplicity of a zero, okay, that is going to be the degree to which the factor corresponding to that zero when the function is written in factored form. Or expressed in factored form. Okay, now let's say that just starting out for identifying polynomials or forming polynomials. And I think that in Alex it stresses more the factored form, whereas I think the book it stresses one form about as much as the other. Okay, so if we're looking at determining f of x in both factored and expanded form, and say we have given and say have for the zeros. Okay, so say we have 1 and 4. And we'll say that the degree of the polynomial, okay, is going to be second order. Okay, now in terms of establishing the factors, okay, so you have your zeros at 1 and 4, and you can determine the factors on the basis of kind of like taking the zero product property in reverse. Okay, so you have like with 1, you have like x is equal to 1, and we have with 4, we have the x is equal to 4. And guess what? So if I sort of take this in reverse, okay, so you have like if we have a 0 at 1, you have x equals 1, we can say that that x equals 1 can result from having set to 0 the binomial x minus 1. And likewise with x equal to 4, we can say that that can stem from x minus 4. And so for what we have in the case of the factored form, and say that we have f of x is equal to, okay, so you have x minus 1. And likewise for the other factor, x equals 4, you say that originates from setting to 0 x minus 4. So the factored form, we're going to have f of x is equal to the quantity of x minus 1 times that of x minus 4. And for the expanded form, okay, this will be if you take the FOIL okay, so you have x minus 1 times x minus 4. So again, we have x times x, so this will be x squared. Outside product, we have it negative 4x. Inside product, we have it negative x. And we have negative 1 times negative 4 is going to be a positive 4. So for the expanded form case, you're going to end up with f of x is equal to x squared. Okay, now we have negative 4x minus x, so this will be negative 5x. We have followed by the addition of 4. Okay, so the factored form we have to consist of x minus 1 and x minus 4. The expanded form, again, this is just with the everything laid out. Okay, so we have x squared minus 5x plus 4. Now, let's say that if we increase the number of zeros, and we'll say that we have at negative 2, 0, and 3. And we'll say that the degree of the polynomial, okay, so that's going to be a third order. Okay, so it's kind of like working in reverse. Okay, so if you have x equal to negative 2, you say this is going to originate from setting equal to 0, the binomial x plus 2. Guess what? With 0, we have just plain x is equal to 0. And for the 0 value of 3, we can say this is going to originate from setting equal to 0, the binomial x minus 3. So you have, in the case of the factored form, so we have f of x. And it really doesn't matter what order you place these. I'm just going to, so you have x plus 2 as a factor. And we have, from 0, I have just the x factor. Nothing is added, nothing is subtracted. And for 3, okay, we have x minus 3 as a factor. So a factored form here, you have x plus 2 multiplying x and x minus 3. And for an expanded form, so you have for f of x, and what I can do here is multiply the first two factors out. So you have x times x plus 2 I'll just do this once more. Yes, if I multiply x and x plus 2, so I'm going to have x squared plus 2x. And I have waiting to be multiplied. Okay, we have x minus 3. And foiling things out. Okay, so you have x squared times x. So this will be x cubed. Outside product, okay, we have it minus 3x squared. Inside product, we have it 2x squared. And the last product, we have 2x times negative 3, so this will be at negative 6x. So we have an expanded form for the function that has those zeros as well as the degree. We have that f of x is equal to x cubed minus x squared minus 6x. Okay, and notice, okay, we have the degree. Okay, so we had a third order polynomial, okay, defined by x cubed, and we had a second degree polynomial where we had the defining term in the expanded form to be x squared. Okay, now in terms of now so far we have the number of zeros and the degree to be the same, and let me take, and it will not always be that situation necessarily. But let me just kind of take one more case here. So we have with the zeros. Okay, so we'll say we have 0, negative 2, negative 3, and 1. So we got 4 distinct zeros. Okay, so we got fourth degree. And we say that with the factors. Okay, so if I have like from 0, I'm going to have x. If I have like x is equal to negative 2, I can say that comes from setting x plus 2 equal to 0. And with negative 3, I can say that originates from setting, say, x plus 3 equal to 0. And we have for 1, you can say that comes from setting...
I can't get the answer to that on Apple Watch.
Sorry. So you have from setting equal to 0, you have x minus 1. Okay, so we have, in the case of the factored form, okay, so we're going to have in the mix, okay, so we have x times x plus 2 times x plus 3. And we have times the quantity of x minus 1. Okay, now if we look at, okay, just the expanded form, so we'll take here, okay, so I'm just going to do a little bit of clustering here. So we say we have an x times the quantity of x plus 2. Okay, so I have x squared plus 2x. And say if I kind of sandwiched together, multiplying x plus 3 and x minus 1. So we have x squared. Then you have minus x plus 3x, so we have plus 2x. Minus 3. And in terms of the follow-through, what I can do is I can take the box method or the geometric FOIL approach, and you have x squared plus 2x is either row heading or column headings. And what I'll do here, I'll just say for the column headings, I'll let this be x squared and 2x and negative 3. And for the row headings, just have this as x squared plus 2x. So you can set this up as either a 2 by 3 array or as a 3 by 2 array. Okay. So looking at multiplying the corresponding parts, okay, so you have x squared times x squared. So this will come out to x to the 4th. And then we have 2x times x squared. Okay, so this is going to be 2x cubed. For the middle column, we have 2x times x squared. Okay, so this will be another 2x cubed. And we have 2x times 2x. Okay, so this is going to be 4x squared. Then for the last column, so I have minus 3x squared. And the last part, we have negative 3 times 2x, so this will be a minus 6x. So we have in the expanded form, okay, so just again gathering what we have here. Okay, so taking, okay, so you had the leading term. Okay, so you have x to the 4th. And we have an x to the 3rd. So we have 2x cubed plus 2x cubed, and that is going to form 4x cubed. And we have, in terms of x squared, so you have a positive 4x squared and a minus 3x squared. So that's going to leave us on the plus side at x squared. And finally, we have in the mix, we have the subtraction of 6x. So the expanded form of what we have for this one is square upon, we have f of x is equal to x to the 4th plus 4x cubed plus x squared minus 6x. And let me just mention, if you're looking at solving for x, okay, so if you had set x squared minus 5x plus 4 to 0, you would have the solutions for x to be 1 and 4. And had I set x cubed minus x squared minus 6x equal to 0, I would have negative 2, 0, and 3 among the solutions. And in this particular case, if I set this particular polynomial to 0, I would have 4 distinct answers that would set the function equal to 0 with 0, negative 2, negative 3, and 1. Okay, now, okay, so far we've had the number of zeros and the degree to be one and the same. Now, just to kind of do a little bit of a change up. Now let's say if we have for the zeros, okay, so if I have 0 that has a multiplicity of 3, and I have 1 with a multiplicity of 2. And say that I have the degree of the polynomial, okay, to be 5th order. Okay, now we have with the factors. Okay, so now from 0. Okay, so if you think of setting x to 0, so we have the x factor. And if I have like 1, say x minus 1 will stem from setting equal to 0, the binomial x minus 1. Okay, but now with multiplicity tied in, I want to have not just x, but x raised to the 3rd power. And with 1, which has a multiplicity of 2, I'm not going to have just x minus 1, but what is going to be x minus 1 raised to the 2nd. So you have, in the case of the factor form, so corresponding to 0 with a multiplicity of 3. And for f of x, so this is going to be equal to x cubed. And again, corresponding to 1 with a multiplicity of 2, I have times the quantity of x minus 1 raised to the 2nd. Okay, so here's the factored form. Now if I look at expanding, okay, so you have x cubed times the square of x minus 1. Okay, so x cubed, that's a standalone single term. Now for the square of x minus 1, this is going to be x minus 1 times itself. And for what we have in the case of x minus 1 times itself, okay, that's going to be x squared. You got minus x, so this will be minus 2x. Negative 1 times itself, so this is going to be a plus 1. And we have for the expanded form, okay, so we have f of x, okay, and we have x cubed over x squared, so this will become x to the 5th. X cubed over negative 2x, so this will be minus 2x to the 4th. And we have finally plus x cubed. Okay, so here we have a 5th degree polynomial. And if I were to set this equal to 0, okay, I have only 2 solutions, one of which will be at 0 and the other which is going to be at 1. All right, and let's say that just for the next few moments, okay, let's see what we get for let me mention this. Tell you what. Simply looking for the factor and expanded form of f of x given. And we'll say that we have let's say we have for the zeros. Okay, we'll say that we have let's say we have 0 is going to have a multiplicity of 2. And then we'll say that we have -4 and 2. And just -4 and 2, those would just be with a multiplicity of 1. So those corresponding factors will not be to a raised power. And we'll say that for the degree of the polynomial function, that is going to be equal to 4. So just for the next few moments, let's see what we get for the factor or a version of the factored and expanded form of the polynomial, given we have the zeros at -4 and 2, and 0 is the only one that has a multiplicity of 2, and -4 and 2 have a multiplicity of only 1. So let's see what we get for these versions of the polynomial. Okay, just looking at what we have in terms of laying the foundation. Okay, so with the zeros alone, okay, so with 0, okay, just at that, okay, we have x. With -4, we can say that originates from anything that involves the binomial x plus 4. And we can say that 2 originates from setting to 0 the binomial x minus 2. So again, like if x minus 2 is 0, x equal to 2. If x plus 4 is equal to 0, we have x equal to -4. And again, with x, we just have the x is equal to 0. Now we have 0 has a multiplicity of 2. So we have, again, not just x, but x raised to the second. So we have, in the case of the factored form, okay, so we have f of x is equal to x squared times the quantity of x plus 4 times the quantity of x minus 2. And for what we have looking at expanding, and you can kind of do this in most any fashion, since the only operation we have between the factors is multiplying. Okay, say if I distribute x squared over x plus 4, so x squared distributed over the quantity of x plus 4. Okay, so this is going to be x cubed plus 4x squared. Okay, we have weighting. Okay, we have to be multiplied. We have the binomial x minus 2. And so we have foiling out. So you have x cubed times x. So this will be x to the 4th. Outside product, okay, we have negative 2x cubed. Inside product, okay, so you have plus 4x cubed. And for the last product, okay, so this is going to be negative 8x squared. And so one version of the expanded form is going to have the zeros and their characteristics. Okay, so you have f of x is equal to x to the 4th. And the middle terms combined, okay, where we're going to have plus 2x cubed. And then we have minus 8x squared. So you have the formation of polynomials from given zeros and the degree. Now let's say that, let's kind of take as a final case here. Say if you have working in reverse. So if you're looking at determine the zeros and multiplicities. Let's see, we have given. See, we have f of x is equal to x to the fourth plus 4x cubed minus 12x squared. Okay, so looking at what we have in the development. Okay, so we went from, again, from given zeros to establishing factors and then expanding. Now we're going from fully expanded to contracting and then finally determining the zeros and the multiplicities. So we have for f of x, okay, so we have x to the fourth plus 4x cubed minus 12x squared. Okay, now for these three terms, now the greatest common factor is going to be x squared. And factoring out x squared, so I have x squared times the quantity of x squared plus 4x minus 12. And this trinomial I can factor even further. So we have x squared. And say I have times the quantity of x plus 6 times that of x minus 2. All right. And so for what we have in this case, okay, we have for the zeros. Okay, if you notice we have with x raised to the second, so from just the x factor we have 0 value at 0, and with the square the multiplicity is equal to 2. In the case of x plus 6, okay, so we're going to have x plus 6. Okay, if I set this to 0, we have x is equal to negative 6. And guess what? It's not raised to any explicit power. So in this case, the multiplicity would be equal to 1, like x plus 6 to the first. And likewise, we have with x minus 2 raised to the first. And we have third 0 is going to be at 2, and that is going to have a multiplicity equal to 1 as well. So the multiplicity of a 0 is going to be the degree to which the factor corresponding to that respective 0 is going to be raised.